Okay, so for the next part of the presentation, we're going to move on to geomorphic covariance structure theory. So we're finally ready. So here we go. Oh, okay. In general, if you have topography, you have broadly two frameworks, two ways of thinking about the world within which to analyze river variability. The first is a continuum-based approach. It's treating the landscape as a whole. It's a topographic map. We could just query it statistically, like we could assume that each pixel in a digital elevation model or each point in a point cloud is independent and identically distributed and try to analyze that. But already we know that that's invalid because it violates the principles of autocorrelation. So that's not really going to work. We could also turn to geostatistics, and there's a lot that's there in geostatistics. However, statistical approaches, including geostatistical approaches, have a serious negative to their use. And that is that while you can analyze them mathematically and come up with metrics out of those things, those metrics are not inherently tied to physics and geomorphology. So then what you have to do is you have to come up with the math of that stuff. You have to come up with then some math and stuff about the physics and geomorphology, and then you have to relate those two. So that creates a whole nother layer of work. On the other hand, if we were to think mindfully about what spatial variability patterns should exist from physics and geomorphology, then we can come up with analyses that can interrogate that explicitly. And in my career, I found that harmonic analysis, assuming, like sine, cosine functions, or it's more advanced surrogate and wavelet analysis, these can be used quite effectively to understand physical processes. One level more sophisticated from that is coherence analysis, which looks at the correlation in the frequency domain. So if you have signals that are taking place from two different variables, and then you find that they have same frequencies, then you could see what frequencies there is that correlation. And the frequencies may even be offset, leading to what we call crossphase. So if you've never heard of coherence and crossphase analysis, I'm not surprised it's not widely talked about in geomorphology. It was something I learned from my colleague Linda Hinoff, who worked on cycles of deposition in geological settings. So I really appreciate having learned about that during my PhD period. Geomorphic covariance analysis is just a new way of looking at things in spatial series, and I'll be talking about that more. These are all approaches that essentially begin with treating the landscape as a continuum, but it's very important to recognize that there's a whole different way to go, and that's what I call the building block approach. That is that we can come up with decision trees that allow us to take a continuous data set and break it into discrete objects. Landform classification, process classification, inundation zones, vegetation patches, or physical habitat, mesohabitat patches. These are all examples of you start with a pattern of depth and velocity, or you start with topography, and you break it down into these individual blocks. Are there truly these threshold lines between each polygon? No, most likely not, but still it can be very meaningful. And I'm not arguing for or against either of these. In fact, I write a lot of papers using both, the more the merrier. However, you do have to recognize this. You can't build a building block design so easily. In other words, let's say that I have a box, and in the box are a bunch of slips of paper, and the slips of paper have the names Riffle, Pool, Run, Glide, and I got a whole bunch of those. If I take those out and I start tacking them on a board, can I make a river just saying Riffle, Pool, Run, Glide? We don't have software to do that kind of thing. There have been articles that I've seen that are sort of like probabilistic approaches to creating patterns. And, my PhD student Rocco Brown and I wrote an article, How to Build a Digital River, in which we present all the different ways you can make a river. You can make a river from building blocks, but it won't have a three-dimensional topography. And I can envision ways that you could do it, but so far, working from the continuum approach is going to be far more effective and more powerful. So what I'm talking about, again, is like the idea that these are different ways of analyzing rivers, but some ways are more valuable when you carry them forward into the realm of design or for experimental testing of different sort of synthetic topographies where you need to create topography. The continuum approach is far more useful, and so it's really where I'm going to be focusing on now. So again, in the basic building I forgot I had this slide. The basic building block approach, you can have discernible landforms maybe in 1D or 2D, but how do you make a synthetic river with these things? Again, it's possible, but it's just not as good as using a continuum-based approach. The next step is we have some conjectures that underlie geomorphic covariance structure theory. First, we begin by saying that both geomorphic processes and ecological functions are more strongly governed by layered scales of spatial variability and topography than the central tendency of a river averaged over scales. So what does that mean? What am I saying here? What I'm saying here is that when you look at topography, you start at one, you zoom out at some level, and we're going to call that scale. So for that size of a domain, you look at it, and it doesn't matter what resolution, you're going to see one type of structure there. Maybe you'll see the valley walls, and then with a valley at the bottom of it. And then you zoom in to the next level, and maybe you see a floodplain in a channel. And you zoom into the next level, and you see the nooks and crannies of a bankful channel, and you see that there's a baseflow channel. And you keep going down and down and down. Geomorphic processes and ecological functions rely on not only variability at any one spatial scale like the bankful channel, but a nesting, a layering of variability from scale to scale to scale. The term nesting is used in geomorphology. What does it mean? It means something inside of something, inside of something, inside of something, and so on. For example, imagine a small bowl, and you put it into a medium-sized bowl, and you put both those into a large bowl. Well, it's the same thing with topography. You can have a large U-shaped glacially carved valley, and then inside that you could have a variety of things nested down different spatial scales. So these processes are governed by that topographic regime, as I would call it, in the same way that we have flow regime and sediment supply regimes and wood regimes. Those are all input regimes. But it's important to recognize that we have a boundary condition regime too, and it too needs to be variable, not just uniform. But then in turn, while the processes are shaped by that boundary condition, of course they in turn maintain and reshape that as well. So there is a dynamic loop between those two things. So how do we take a river digital elevation model and extract the essential spatial patterns to test these conjectures? Let me just show you an example. Obviously we can't sit here and work through GIS, and I'm not going to show you all the details of all the workflows, but I'll give you a feel for it. So here's a section of a river that my student Xavier found in Southern California. It's along Happy Canyon Road here. I don't know what the name of the stream is, but I like it because it's dry, so we can get the whole topographic structure from LiDAR. And when you look at this, even though it's a small photo, but you have a partially confined valley on the left and then a more agricultural area on the right. We have channels nested within channels, nested within channels in here. So we can begin and we can identify a baseflow channel and the thalweg along that channel. And for this red thalweg line, I've tried to set the width about to what the base flow is. So it's not perfect. I didn't use a model here. I just sort of whipped it up in PowerPoint. But that's basically what that is. And so if we look at the cross section, conceptually the idea here is that, this blue line is the width associated with this red line there. And within that, there can be nested finer nooks and crannies from lower flows. And then, of course, that is in turn nested in within a bankful channel, which is then nested in within floodplains and terraces and so on. Well, we can put cross sections along here, clip them to a wetted area polygon, and extract a width series. And that might look something like this. So this is the width of the river from upstream to downstream in meters. And what you can see is there's a lot of high frequency undulations and then some lower frequency undulations. And so once you have a series like this, we can apply signal processing methods, and whether you prefer wavelets or whether you prefer spectral density analysis, we can do a decomposition of this into its primary constitutive elements. For this signal to replicate it closely, it might take 20 to 100 constitutive elements, but just to give you a feel, here are 5 of them. These are 5 of the top 10 most powered elements, and you can see that they range. So we can reconstruct any series just using these sorts of sine and cosine functions. So even though when we go back to classic, late 20th century landform mimicry where people were literally building sine curves, we don't have to build a sine curve in a river, but we can use multiple sine curves at different frequencies, amplitudes, and phasings to reconstruct whatever pattern we want, if we only knew what pattern we'd need. And this is a process called harmonic decomposition. But it's important to understand that this Baseflow channel is nested within, higher banks that each have their own independent series. There's some amount of autocorrelation, but the farther you go up, then the more decorrelated that will become. So I'm going to skip ahead to then like a flood flow, and I've just crudely drawn a polygon here. It's off the page and I'm sort of bounding it with a road. But imagine we had the wetted area polygon from a 1D model or a topographic detrending and horizontal slices or a 2D model. We have a lot of approaches for that. And then we would have, I'm showing the same Thawag here, but at this point we would probably straighten this out to follow the center line of the inundated area. And then we would draw cross sections across the wetted area. We can now make a width series for this inundation level, which is much higher. And what you're going to see is while there is some high frequency component, it's far less powered. And now we see the structural control from the valley, partial confinement instituting itself. You could also see that the valley is generally widening in the downstream direction. And we can identify the decomposition of this into its constitutive elements. You can see the larger amplitude big elements here as well as then the smaller elements. But again, it might take, say, 20, maybe 8 to 20 to mimic this pattern compared to like 20 to 100 for the other one. So this just illustrates the idea that we can take if you had a DEM of a river, and I didn't show it here, but we do. We have the DEM of this river. You can extract individual spatial series, a width series, a bed elevation series. You could do presence or absence of vegetation. You could do canopy height. You could do abundance of wood. You could do biomass. You could do patterns of deposition and erosion. Like anything that you have a map of, you can make a spatial series of how it is down this river corridor. Let's take a little bit more of a deep dive into some of the specific functions. In my opinion, in the 21st century, the most enigmatic thing that we have to deal with is the concept of detrending. Detrending is the 21st century enigma to replace bankful discharge determination in the 20th century. There's dozens of papers about how to figure out bankful discharge. I promise you that in the next 20 years, we're going to have just as many papers, people arguing over how to do detrending. Detrending is absolutely essential to being able to understand topography, and yet it's quite enigmatic because there's no one right or wrong way to do it. Detrending has different purposes for what you want to get. But in general, what do I mean? What am I talking about here with detrending? Well, here's a plot of, 7 kilometers of a river. It's my Lower Yuba River example. And you can see that, of course, as you go down from the mountains to the valley and down the valley, the river has an overall slope. Well, actually, this is a pretty gentle slope, it looks like, 0.2%. That's not too bad. Yeah, that's not too bad. So we have this slope. And so, the elevation as a whole goes down. If we want to understand geomorphic processes, though, they're not going to depend on our absolute elevation unless you're getting into freeze-thaw territory. But for a case like this, that's like 50 to 80 meters above sea level, the main thing that's relevant here is that the processes are not driven by absolute elevation. They're driven by relative elevation. Are you a pool? Are you a riffle? Like, that sort of thing. Essentially, we need a surrogate of depth to get at the hydrodynamics that's going on here. So in this case, detrending means to just literally remove the line. The line. Now, in order for this to work, ideally what you want to do is you want to start and end as close as you can to the same position in the overall variability function here. In other words, if I start in a pool, I need to end in a pool. If I'm going to start at a crossing point, I should end there. Now you can see we're not quite at the crossing point here. Probably the data is just a little cut off. But anyway, it's coming up. It's pretty close. What you don't want to do is start in a pool and end in a riffle crest, because that would bias the function. And of course, you also need to independently geomorphically identify what constitutes a reach, because we don't detrend across reaches. We're not looking for a nonlinear function. We want to do linear detrending of a single geomorphic reach. So we can come up with this line. Now, when you look at this line function, why do I have a bajillion decimal places here? And one of the things I hope you've learned in your introductory science classes is to pay attention to significant figures. Because on the x-axis, we have numbers that are in the tens of thousands, and then on the y-axis, we're going down to basically 2 significant digits. When you have this loss of information, if you don't have many significant digits, you are doomed. You will never get this line correctly characterized. So it's really, really important where we're doing detrending and all we care about is mimicry of this line that we have many, many decimal places. The R-squared value, it doesn't matter. It just came along for the ride. What matters is that to start from an X, and when you're transitioning across many significant digits, you have to have a lot of detail here. Anyway, this is straight, simple, linear detrending. To me, it's the gold standard of detrending. If something isn't linearly detrending, then the chances are it's not a geomorphic reach. The other thing, though, is there's many other kinds of detrending, and one of those is more of like polynomial or spline detrending. In that kind of detrending, it tends to vary more, like it follows the topography more. When you follow the topography more, what you're saying is that the variability you see is part of the trend, not part of the variability. Like by definition, variability is the deviation from the central tendency. So with a line, we have the absolute minimum loss of variance with this sort of detrending. There may be reasons why you would want to remove riffle pool variability. For example, let's say you were focused on sub-morphological unit scale, boulder structures, large bed elements. Then you might want to remove this variability and just isolate that sort of high-frequency variability. So once we subtract that line, we now have a detrended thing. We're still working in meters, but we have the residual. So this is just get this function and then take the original elevation and put it into x and get y. And then this is a plot of that y, which is the residual elevation. We can then calculate the mean, which ought to be 0 or very close to it. We can calculate the standard deviation. Once we've done this detrending, then we want to standardize this data, which means to subtract, let me get this right, subtract the mean and divide by the standard deviation, which you can see here. I put the formula. So we're going to call standardized bed elevation ZS. It equals the value of detrended elevation at any point minus the mean value of elevation, which in this case is 0, divided by the standard deviation. So you can see that where we've gone from residual elevation values in units of meters, we now have units of 1, 2, 3 that are numbers of standard deviation. In other words, if we look at this function finally, relative to the average elevation, The riffle pool variability here goes from a low of -5 standard deviations to a high of a little more than 2 standard deviations. Now you can begin to see why I don't like reach average metrics in vanilla rivers. If you were to design a river restoration project, you would take the average value, like the average value of this reach would be the representation. Now, oftentimes people might design riffle pool variability around it, but what are they designing and why? Variability is not random, it's governed by geomorphic processes. But the first step is to just accept, hi, I am a river and I am variable. Accept and give into that and work with that natively. When it comes to width, if we're at the reach scale, we're not going to have to do a width detrending because over the length of a the length of a reach, width probably shouldn't be increasing significantly. If it is, it's up to you to decide if you're going to detrend it or not. Of course, if you're going over a very long segment of many reaches with many tributaries bringing in more water, width will expand in the downstream direction. But even that isn't necessarily worth detrending. For the purposes we're going to use it, we need that variance. We can account for that linear growth in width because that has valuable implications. So I want to correct myself. Don't remove the trend in width unless you absolutely have to for the harmonic analysis that you're doing. If you do, keep that linear function that you'll end up using that later. So anyway, we can take the width and we can compute a standardized width as just the width value minus the mean divided by the standard deviation. And again, that gives us units of standard deviation. And here we're going from about negative to 3.5 standard deviations. So a range of 5 standard deviations in width. And we can see that if you do these different horizontal slices of a river from, here's a 20% of bankful stage, and then a flood that's 8.44 times the bankful flow, you see dramatic differences. What this means is that we have width series nested within width series. Like this upper line is completely contained. It's a bowl within a bowl. Except this isn't a bowl, this is a linear thing with all sorts of variability going on here, and then this is within that too. Think about a piano. If I take my right hand, well, of course on the video it's on the left. If I take one hand and I put it on the high keys, beep, 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 and I take my other hand and I put it on the low keys, do, 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 I can play both those at the same time, boo, 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 at the same time. You can't have multiple sound at the same time at different frequencies, amplitudes, and phases. And rivers are the same. You can have one thing nested within another. That is the key to this whole thing. And these patterns are so radically different. What happens, the geomorphic processes depend on this nesting. We have to understand that nesting and then control it in design. Okay, so let's just now take these basic width series and make a reconstruction. And let's see how good we can get with this. So I want to show you an example from the South Fork Eel River in North Coastal California. We have a site among our database at site 316. When you look at the photo of this site, you first are impressed that it is a cobble, small boulder kind of river. You see that during the summer we're at a base flow, and then that base flow is nested in with some kind of bankful channel, which is then in a highly confined valley or canyon. So I want to make a reconstruction of the combination of the base flow and bankful channel and not worry about the valley pattern right now. So the first thing we can do is we can go out to this site and we can survey it with a total station. This is feature-based surveying, which means it's not like a billion points like LiDAR or drones or something, but it is a complete representation of the morphology of the river, down to say the 2 to 3 meter scale. And so that gives us this. Water's flowing from left to right with blue at the lowest elevation. Now what I can do is I can do the same kind of procedure like I showed you from Happy Canyon Road. I could run a thalweg down here. I can make cross sections along here, and I can extract width series. And I can do that for each stage of interest, in this case, base flow and bankful stages. When I do that, I then have to have some way of taking those and creating an archetype. And to do that, we use our software River Builder, which is available for free on GitHub. This presentation is not going to present River Builder. So maybe you've already seen some River Builder presentations or not, but right now we're focusing on just these variability functions. So when I do it, right now we get to this, and I want to give credit to postdoc Dr. Anzi Lee, who made this representation. We kind of did it as a team-based approach. So right now I want you to focus on 3 attributes of this thing. First, there's a Baseflow channel. Its width series is exactly following the width series of the Baseflow channel in this upper image. Second, we have a bankfold channel, and it too is following the same series. And then finally, we have a bed undulation series, and it too is following the same thing. Now, there's one wrinkle to this, and that is that in the real thing, there's a channel asymmetry. That is, the channel is preferentially on the right, then on the left, and then on the right again. So that we have a Baseflow meandering here. And in this archetype, we could have, but we have not replicated the structure of the meandering. We just did one simple sine curve for this in this case. And associated with that, we also had made a symmetrical Baseflow and bankfold channel. River Builder has the ability to make asymmetrical left and right conditions, but we didn't go to that level of complexity. Also, I don't think this isn't colored the same way. As you can see, like we have a different green out here rather than that. So I don't think you can look at the colors per se. And then finally, you can see that within the Baseflow channel, we have a roughness function here that is replicating this kind of roughness that you see from this sediment. So overall, we have a lot of things going on here. And we've created an archetype. An archetype means it's not a perfect replica of the thing, but it's captured the essence of that thing. So this is just an example of how we can take individual spatial series, harmonically deconstruct them, put them into software, and make an archetype that replicates that. Why would you want to do that? Well, what if you want to create numerical experiments to run hydrodynamic modeling, morphodynamic modeling, ecohydraulic modeling, or whatever to try to understand how a system works? Or maybe you're going to create a flume archetype, and in the flume you're not going to perfectly replicate it. You might want to use something like this to help design the flume. Okay, so now we're going to move on to the next level of sophistication. In that harmonic deconstruction and reconstruction, because we were using a real site, ultimately the width series between Baseflow and bankfold were locked because we were just replicating the real site. But it's important to understand that across different variables like bed elevation, width, or anything else, or for any one variable at different nesting stages, that there is a interlinking there as well. Let me illustrate this with going back to our Yuba River example. Here I'm showing the 2 standardized spatial series. The red line is the detrended bed elevation series, and then the blue line is the standardized width series. What you can see is that these 2 things are going up and down pretty closely. They're not in perfect lockstep, but it's pretty darn close. It doesn't have to be perfectly correlated, and indeed there's one place where it's completely opposite. But the fact that on the whole the river is going in lockstep is no accident. This is a result of the driving morphodynamic process governing this river that I'll be getting towards shortly. This linking is the core of what geomorphic covariance structures is going to be all about. Let's look at it another way. In here I just showed you a correlation for one flow that was a Baseflow. So, we can now look as the x-axis is how many times bankfold discharge we are, and the y-axis is our correlation coefficient between the bed elevation and the width series. And you can see that, and this is also by reach, but let's just simplify it and look for the segment. We can see that the correlation is at a peak for the segment as a whole at bankfold discharge, in this case, of about 0.6. There are individual reaches that go substantially higher, up to 0.8, And there are other reaches that reach their peak at 2 times bankful. But generally, between 1 and 2 times bankful, we've seen consistently a peak in the correlation between bed elevation and width. All this means is that these two variables are strongly related to each other, and this is true across most flows. There's a few cases where it's not, but across most flows, there's a very strong relationship between bed elevation and width because they're coupled together. And here's one example, I should say, where it reaches a peak at a much higher flow, but this is a pretty regulated reach. Okay, so I'm showing you evidence that different variables are linked together. So that finally brings us to geomorphic covariance structures.